Hi everyone. As previously announced, this lecture is going to be posted online because today's the Winter Technical Conference. And I have a recording from a previous semester, and I'm just going to edit these announcements into that. Let's look at these announcements first of all. Homework number 2 will be due on Tuesday, the 29th of January. And so you've got that list of problems. That's also on the course schedule. And then on the 31st of January, on Thursday of next week, we're going to have our first quiz of the semester. And the coverage on that is going to be all of the class lectures up to and including the Tuesday, the 29th, and then the corresponding homework assignments that you will have completed. And so just to put that on your radar, we have our first quiz. The subject of today's class lecture is empirical resistance equations. Now this is a recording that you're watching. I'd encourage you to pause the lecture and actually work through the examples. When it's a hand calculation example, pause the lecture and work through that independently, and then check your work to see if it matches up with the example solution that I bring up on the screen. Don't just rely on my calculations. And then this lecture also has a problem where you're going to be working through an example using Microsoft Excel. And so for that problem, what I'd suggest is that you run Microsoft Excel in one window and then kind of follow along with the recording in another window. That way you can get the experience of that example. So today specifically we're going to be focusing a little bit more on the Hazen-Williams equation and Mannings equation to complement the information you've already received on the Darcy-Weisbach equation. And then there's an example at the end that kind of ties it all together and compares and contrasts those three empirical resistance equations. One last note before we get into the material. The order of the slides that you have printed out may be slightly different from the order that they're presented in this lecture, and I hope you're not alarmed by that. It's just I changed the order of a few things over the semester, and this lecture happens to have it in the old order. So you'll just need to jump around in the notes a little bit compared to how they're ordered in your handouts. So anyways, if you have any questions, please feel free to stop by during my office hours or send me an email, and I hope you enjoy the Winter Technical Conference that you're attending today.
Some tips for the homework assignment you've got due on Tuesday. As you start working on these, I think each one of these little comments will make more sense to you. But I did want to point out that they're there. We had water being directed through this spigot, and what causes the pressure is a tank higher up on a hill. And so we have to think about where is the energy going. The energy at this tank, at the origin, is potential energy, and it's causing pressurization downstream, and it's also giving up energy to losses. And what the Hazen-Williams equation, which is shown here, helps us to calculate is the losses side of things in an easy, direct way. And so when you substitute in the velocity, let's see, I think the velocity you should have calculated is 1.4 meters per second. Is that right? All right. So if we have a flow velocity of 1.4 meters per second, we substitute that into the Hazen-Williams equation and get 17.54 meters of losses. So the elevation difference between the two is going to account for the pressure. We have 103.5 is the upstream elevation, the downstream elevation of 55, and then the losses, which means there's leftover head in the amount of 30.96 meters, and you multiply that by the unit weight of water, and we get it should be about 303 kilopascals at that tap. So the Hazen-Williams equation shows up a lot on the FE exam because it's tough to give iterative problems on an exam where each question is only supposed to be, on average, 2.9 minutes. So you probably won't see anything related to the Colebrook equation on the FE. But you probably will see something related to the Hazen-Williams. Yeah?
I know in fluids you told us to assume 9810.
Yeah.
Now where this is outside, are we supposed to assume 9790 to do that?
Well, as long as you just state what assumption you're making, then that's fine. I mean, there's different arguments to be made. You know, the water that is going to be coming out of a groundwater, or out of a pipe that's underground is probably going to be pretty cool. I think maybe around 55 or 60 degrees, and so you could look up the unit weight for that. This maybe, the 9790 corresponds to a little bit warmer water, and I think the thinking there is it's in a tank, and so it's warm from having been in the ambient air. Your question in the back? Yeah. Mm-hmm.
Yeah, so the Hazen-Williams equation is easier than Darcy-Weisbach.
Yeah.
Why do we use Darcy-Weisbach?
That's a great question. The last example we're going to work today compares the two, and it shows that the Hazen-Williams equation is easy, but you sacrifice some accuracy. So for instance, when we're using WaterCAD or WaterGems for design, we don't care if it takes the computer a few extra cycles to converge on a solution for F, and so we'll always tell it to use the Darcy-Weisbach equation for calculating its head losses. But you know, if you've got only 2.9 minutes to come up with an answer, then the Hazen-Williams equation will do a great job, and it's pretty direct. But the main reason why we don't always use it is it's not as accurate. And also, there are limits on the range of conditions that it can be applied to. The Hazen-Williams equation is limited to pipe diameters from 50 millimeters to 1850 millimeters, and it's for a specific temperature. Technically, it's only calibrated for water at 16 degrees Celsius, and the velocity flowing through the pipe should be less than 3 meters per second. And so that's a pretty specific thing. As you get further away from 16 degrees Celsius, that introduces error. Now, your previous experience using the Hazen-Williams equation was in the lab on the pipe rack, right? And each one of those pipes was smaller than 50 millimeters in diameter. And so some of the trouble that you had in comparing observed behavior to expected behavior based on the predictions here is just that the pipes were too small to be really accurately modeled with the Hazen-Williams equation. Whereas the Darcy-Weisbach equation isn't at all troubled by smaller pipes or a specific flow velocity or a specific temperature. It's a little bit more flexible. So the Darcy-Weisbach equation is the most accurate, it's the most flexible, but it's tricky because the F value sometimes requires iteration. The Hazen-Williams equation, which you've had the chance to solve a little bit today already, only is valid under certain circumstances. It's easier to use because the roughness factor is constant. So here are the different ways that it's written. The first one that we've already done solves for energy loss due to pipe friction in terms of the C value and in terms of a certain known velocity. Another way, if you rearrange this equation, then you can find what is the velocity for a certain slope of the energy grade line, S sub F. And the S sub F, the definition of that is the head loss due to pipe friction divided by the pipe length. So the slope of the energy grade line is what you put into this S sub F function. And you can see that there is a different formulation of the equation if you're working in the traditional British gravitational units, because the C sub H values are still the same, but you'd be putting in units of feet into the hydraulic radius instead of units of meters, and units of feet into the length instead of meters, and so on. We already did this example where you were finding out what's the pressure at the junction, but let's look at the same picture with a different question. What if we have this elevated tank and water is going through the pipes? We want to find out what's the maximum flow rate that you can have. The previous example, when we calculated that the pressure would be, was it 303 kilopascals? That means that not all of the energy was being used to overcome pipe friction. Some of the energy was being left in reserve so that there would be pressure in the pipe. If you exchange that energy, instead of keeping some of it in reserve to pressurize the pipe, and you spend it all on overcoming pipe friction, then you can move the water at a faster flow rate. Remember that this was potential energy. The water in a tank up on a hill is potential energy, and we're transforming it into movement, which causes pipe friction, and then pressure. So in this next example, we're going to use the other version of the Hazen-Williams equation. And it's the same 760 meter pipe length, the same unit weight of the water. The material is still cast iron, so it'll be 130 for the C sub H. We want to find out what's the flow rate that you can achieve under these circumstances. What's the Q value? And so remember, the definition of S sub F is the head loss, H sub F, divided by the pipe length. And in the energy equation, we're going to say that the H sub F is 103.5 meters minus 55 meters. And so all of the energy difference is going into the pipe friction. And there won't be any pipe pressure right at the end of the pipeline. There will be pressure upstream of the end of the pipeline, but at the end of it, at location 2, which is right at the spigot, then there's not going to be any pressure. So see if you can find the flow rate in the circumstances that are described here, just by substituting into the Hazen-Williams equation. Anybody remember what's the hydraulic radius of a pipe that's full? That's right, D divided by 4. All right. So it should be 19.2 liters per second is the maximum we can get out of that system as it's pictured right now. If we put a pump in the line, then that would increase the flow rate. But just based on the difference in elevation, you know, the driving force there is the potential energy of the water at location 1 is higher than location 2. So all we can get is 19.2 liters per second. I'd like you to draw the energy grade line for this. Because I think there's a concept that probably some people aren't getting yet. And it's a little bit tricky. Remember, the energy grade line shows you how much total energy there is at all points in the system. And so if we're starting at the tank, just do a little sketch. So we've got, here's the ground elevation, here's our tank. All right, we know that the EGL starts at the water surface, and the EGL is independent of the pipe. So the pipe is going, all right, and here's the pipe coming out. But in the beginning, let's say here is the valve. All right. So the EGL is going to look like this. It's this dashed line. And we know the EGL should end, if there's water coming out, then it'll be slightly above the water surface because it still has some velocity head. But I wanted to point out the fact that the EGL is coming along and then there's a sudden drop. And then it's above it again. This sudden drop is the energy that's lost as the water flows through the valve. And so that explains why when we were doing the first problem, we calculated there was 303 kilopascals of pressure available. Like if you connected a hose to the threads on that valve, then, you know, and you opened it up and measured the pressure that's available as the water is flowing is the 303 kilopascals. But if you take the hose off, then there's zero pressure as the water comes out and is just in contact with the atmosphere. But just on the other side of that valve, now there's water pressure that is available. And so like suddenly you're just losing pressure, and the elevation didn't change, and the velocity on one side of the pipe is the same as on the other side of this valve, and so it's literally like a local loss where you're losing all of the remaining pressure head as the water flows through that valve. And so if you draw the EGL drawing for when the valve is partly closed, then it would be like a sudden drop. But now in this next case where it's free flow, like if this valve is all the way open, then the energy grade line would go straight from the water surface down to just slightly above the water surface after the valve. So depending on how we open or close the valve, that either will introduce a local loss or eliminate it. Any questions about either of the two examples we were looking at? All right. Well, another one of the empirical loss formulas is called the Mannings Equation, and it's also easy to calculate because the friction factor doesn't change as a function of flow rate. It's a constant. Instead of the variable c, in Manning's equation, the friction coefficient is given an n. It can be used, technically speaking, it can be used for closed conduit flow, like we're doing in this section of the course, but more commonly, Manning's equation is used for open channel flow, like flow through channels or flow through pipes that are partly open. So this drawing on the right is showing a circular pipe that's only partly full, and then above the water surface would be air. And an example of that is a sewer, either a sanitary sewer or a storm sewer. They flow by gravity, and so what they really are is they're circular channels that aren't under pressure. But here is Manning's equation expressed in terms of velocity. It's also common to have it expressed in terms of flow rate, and then all you have to do is just multiply the right-hand side by the cross-sectional area. But the SI units, you don't have to multiply it by this 1.485 in the same way that you do for the BG units. Now, S sub F means the same thing that it did before. It's the slope of the energy grade line, and so that's the head loss divided by the length of the pipe section. Here's a table that compares typical C values and typical N values, and let's use those in a comparison of the three different methods. The Hazen-Williams, Mannings, and Darcy-Weisbach. The Darcy-Weisbach is the gold standard in accuracy. And if we really wanted to be picky, instead of using Jane, we could use the Colbrick equation, but Jane does a pretty good job as we've previously demonstrated. So let's find out for water flowing through a pipe that's ductile iron at a velocity of 1 meter per second, then what's the head loss over 500 meters of pipe, according to each of the three methods. Now let's get the C values and the N values that we're going to need. So method A, it says to use the C value of 130, method B, the N value 0.013, and then for the Darcy-Weisbach, assume the equivalent sand roughness of 0.26 millimeters. Okay, so calculate the head loss according to all three methods, and then we'll see how close they get to Darcy-Weisbach. The Manning one's bad. For closed conduit flow, it's not at its best, but it's pretty good at open channel flow. Yeah, Manning did bad.
What's the exponent of the natural log on the bottom of that one equation?
Yeah, squaring it after for the F value? Yeah, square. So the F value you should be calculating with the Jane equation is 0.024. And then when you substitute that into the Darcy-Weisbach equation, you should get 4.08 meters. We can think of that as the most exact of the estimates. And the Hazen-Williams is pretty close. 4.08 we can think is the accurate answer. 3.85 is fairly accurate. Manning's equation is wrong. But if you're looking for the silver lining, at least it's conservative, right? It's going to overestimate the head loss instead of underestimate the head loss. And in a design situation, you'd want to overestimate the head loss so that you can make sure that you provide adequate pressure rather than underestimate it. Talking about how big should the pipe diameter be? Last time in class, we rearranged the Darcy-Weisbach equation in terms of an unknown D. Here's an application that we're going to combine that formula with the energy equation to find out how big should a pipe be in order to achieve a required flow. The diagram here shows that there is an elevation difference of 35 feet, and we're pumping from the lower elevation to the higher reservoir. And there's 800 feet of pipe length that is causing some pipe friction. And so at its heart, this is an energy equation example where reservoir 1, our obvious place to pick as location 1 would be the surface of that tank, because then that allows us to say that the velocity of the liquid is 0. It allows us to say that the pressure is 0 because it's exposed to the atmosphere. And the same thing here at location 2, at the destination, the velocity of the water inside of the tank is 0, and the pressure up at the surface is 0. So that simplifies this equation into saying that the pump head that's being added is overcoming the friction losses and the elevation difference. So we've got Z1 plus H sub P is equal to Z2 plus H sub F. So the reason why we have to add the pump head is because of the delta Z plus the H sub F. Now H sub F is a function of the flow rate. So the faster the water is moving, the more pipe friction there's going to be. This equation that we saw last time, rearranging the Darcy-Weisbach equation in terms of D, remember what we did there was we said we don't know what the velocity is, but if we put in the flow rate Q in the numerator and A in the denominator, then that's the same as velocity from a numerical standpoint. And so solving for D, but the tricky thing is that F value is dependent on the diameter. And so what we're going to go through is an Excel example of how you can find out what pipe diameter needs to exist when there's a pump involved. The pump, 10 horsepower pump, by the way, if your pump is described in terms of horsepower, then you can rearrange the horsepower equation to solve for H sub P. And we'll do that in the example because it's the H sub P that you have to put into the energy equation, not horsepower. And unfortunately, HP and HP, sometimes it's easy to make a mistake and confuse the two, horsepower and pump head. Here, this is the kinematic viscosity of water and, of course, the Jane equation for the friction factor F. So if you have Excel available, why don't you start that up, and let's work through this one together. All right, I'm going to paste the formulas into Excel just so that they're handy. The friction equation, horsepower, and the diameter equation. All right. Okay, so This is going to be several iterations that we're going to have to do, but first of all, the horsepower. If we rearrange the horsepower equation to solve for pump head, that's going to be H sub P. The pump head is 550 multiplied by the horsepower divided by the unit weight of the liquid multiplied by the flow rate Q. And then that'll give us the horsepower in terms of, the pump head in feet. Okay, so what we have is 10 horsepower. The cast iron pipe gives us the equivalent sand roughness here. Let's see, cast iron, so 0.00085 is the epsilon. In terms of feet is 0.00085. Okay, the unit weight, gamma, in terms of pounds per cubic foot, the typical unit weight for water, 62.37 pounds per cubic foot. And the kinematic viscosity in feet squared per second was given as 1.22 times 10 to the minus fifth. The flow rate is 1.5 cubic feet per second. All right, so let's calculate the pump head in terms of feet by substituting in the values to the equation that I wrote on the whiteboard. This one. So that is equals 550 times horsepower divided by the unit weight divided by the flow rate Q. Okay. Now if we've got the length of the pipe is 800 feet. All right, so we can calculate the F value the first time around using the Jane equation because we've got the, I guess I haven't typed in the diameter yet. The pipe diameter in feet here is, it's unknown. So we have to start with a guess. And what you can do when we have to start with a guess of the diameter in order to calculate the first F value. And there's a number of strategies there. One is just to say, well, maybe it's 1 foot in diameter, and then find out what would be the Reynolds number based on the flow rate, what would be this relative roughness term, and so on. Another approach is just to start with a guess value of F, just drawing it out of thin air. And let's take that approach. Let's just say we have a guess value of F the first time around of 0.01. And if we have that, then we can calculate what the diameter would need to be for a guess value of F. So this is the diameter in feet which we're calculating based on the guess. So 8 times L times Q squared divided by H sub F. Yeah, we need to calculate H sub F for the delta Z. This is another place where you just sort of jump in with a guess. And so assuming that we have the pipe friction of 0.01, then that's going to require a guess of the pipe friction we'll initially just say is 0. And so we'll say that all of the energy goes into lifting it. So it seems like I've stumped myself here today, guys. Let me pull up the example that I built this on. Well, what's that? Mm-hmm. Let's see, I guess that's direct, right? It's not a guess, right? Okay, good call. Sometimes you can't see the forest for the trees. So yeah, let's put the energy equation on the board. That solves all confusion. So we've got the delta Z. Yes, thank you for leading me back on course. The delta Z is 35 feet. The 35 feet, the H sub P we calculated is what, 58.79 feet? Is that what it said over here? Yeah, okay. So then the H sub F that comes from that is going to be 23.79 feet. That's how much energy we can spend. You can think of it as like we're spending it on the frictional losses. All right, so back here to an H sub F term in terms of feet. It would be the pump head minus the elevation difference of 35 feet. All right. 8 times the length times the flow rate squared divided by H sub F divided by G, so 32.2 for traditional units, divided by pi squared. And we also need to multiply by F. Well, it saves me from having to put parentheses, you know, because I've got 3 terms in the denominator. I've got H sub F, G, and pi squared. So I can divide by them, multiplied by each other, or just divide over and over again. It's like a little shortcut I sometimes do in Excel just to confuse students. Eventually it'll confuse me too, so it'll be payback. All right, so I'm going to use that guess value of F and take it to the power of 0.2. All right, so this is what the diameter of the pipe would be if it was this guess value of F. And so now we'll get an area of the pipe based on that. The area is just going to be pi times d squared divided by 4. And then the velocity that would arise from that if we have the Q divided by the area. And finally, a Reynolds number, which is unitless. So it's going to be velocity times diameter divided by the kinematic viscosity. All right. Now that we've got a guess F value, this is like a better guess of the Reynolds number, and we can use that to calculate an improved F value. So this F value is from Jane. It's not just like a raw guess in the same way that the first one was. So now I'm going to type in the Jane equation, 1.325 divided by the logarithm of K sub S to D. So K sub S is the same thing as epsilon. K sub S divided by 3.7 divided by D plus 5.74 divided by the Reynolds number to the power of 0.9. And don't forget to square it, which is easy to forget. So this is a slightly better guess than just the out of the blue 0.01 that we started with. And the nice thing is once we've got these equation typed, I should anchor them because I want to just be able to copy and paste over and over again. So I'm going to anchor everything except for that reference to F. So I'm going to anchor the references, everything except for the pipe friction. All right. The same thing with the area will be looking above it. The velocity, I want to always look at the flow rate. So I'm going to anchor that. And anchor the reference to kinematic viscosity. Okay, so I can copy all of these, Control C, and paste them with Control V. And then it's looking at the new F value to calculate an updated diameter. And what we do is we keep iterating this until it doesn't have any differences in the diameter anymore. And so we can copy and paste again. Something went wrong in that step. I think something wasn't anchored that needed to be. Oh yeah, in the Jane equation. All right, so I need to anchor the reference to epsilon in the Jane equation, but everything else I think we do want to be relative. Yeah, that's right. Yeah. F4, once you're in the cell that you want to put in those dollar signs. Oh, still it's screwed up. Oh, it's because it, yeah, okay, I need to just copy it over again. All right, there, that's better. Okay, so here's the F values. So they're not changing as much. The first one, it went from 0.01 to 0.023, then it's a smaller adjustment in the second step, and if you look at the diameters, it's just sort of a minor convergence. And if we did another step again, then the diameter basically isn't changing anymore. And one more iteration would confirm that, 0.535. So that tells us that if we make the pipe diameter this size, then we're going to get the flow rate of 1.5 cubic feet per second when we pair it with this pump. Any questions on the numerical part of this using Excel? The whole reason why we had to do it was because we didn't know the F value. The reason why we had to iterate was because when we started off we didn't know the velocity through the pipe, and so we couldn't say with certainty what the F value would be, but by starting with a guess we were able to hone in on what the F value would be. Yeah?
So after we do this, we jump to the next pipe size, right?
Yeah, good question. So it's not likely that we're going to find a pipe that's actually 0.535 feet in diameter. So we're either going to have to put in a bigger pipe or a smaller pipe. Let's look at this picture. So if I made the pipe bigger than 0.535 feet, what's going to happen with nothing else changing? Just the pipe is bigger than what was required by that diameter formula. What is it? So, it's the other way, actually. You make the pipe bigger, then the flow rate is going to be bigger than 1.5 cubic feet per second, because a bigger pipe diameter means that there's going to be less resistance. And so actually the system will pump faster than it can if the pipe is smaller. So if we decided to round down, if instead of this required diameter of 0.535, if we just put in a 6-inch pipe, which is a half-foot diameter, then we wouldn't get 1.5 cubic feet per second. The flow rate we could get out of a smaller diameter pipe would be lower because there's going to be the same amount of energy loss. There's going to be 23.79 feet of loss, but it's just that we would arrive at that loss at a slower velocity with the smaller pipe diameter. So I'm glad you asked that question. What we'd probably want to do is ask what's important to us. Is it important that we exactly get 1.5 cubic feet per second? And if it is, if we have to have exactly that flow rate, then we're going to need to have a bigger pipe and then a valve so that we can control the flow rate that's actually delivered downstream. So the valve, we'd close the valve a little bit until we got the flow rate that we needed. But if the client says it doesn't have to exactly be 1.5 cubic feet per second, you know, you could save a lot of money going with a 6-inch pipe instead of an 8-inch pipe, then maybe a little bit lower flow rate would be fine. And that's what they'd select.